Hello, welcome back. In this segment, I will show how we can decrypt block of ciphertext using the padding oracle we discussed in the previous segment. Okay, in the previous segment, we learned how to find the number of padded bytes using the padding oracle. Now we will take that idea one step further. We will decrypt a particular block, okay, just any block in our ciphertext. So remember, ciphertext is public. This whole thing is public, okay? The IB is also public, okay? That's the assumption we are going to make. We don't know, of course, the key. And the goal is to recover the plain text just using the ciphertext and the IB without having the key, but using the padding oracle. Okay, so for that, I need to introduce something called lost word oracle. Okay, so let me proceed now with the definition of lost word oracle more formally. What I'm going to do is I would like to learn the plain text corresponding to one particular block of ciphertext. Okay, so this is one particular block of ciphertext, right? And don't worry about the number of boxes I have put here. This is 6 here, but if you're using AES, you'll have 128-bit. If you're using DES, you will have 64-bit and so on. So don't worry about the number of boxes, but this is just a block cipher. Okay, one particular block of ciphertext is shown here. What I'm going to do is I'm going to answer this question. What are the bytes of the output of the decryption algorithm? Of course, we don't know the key. Okay. The question is, can we find as many bytes as possible when this ciphertext block Y is decrypted? We don't have access to the key again, but use the padding oracle to learn these bytes. That's what I'm going to do. For that, what I'm going to do is generate a random block R, just a bunch of random bytes. And then I'm going to call the padding oracle. The block R followed by block Y, that's the meaning of this line, is valid. Okay, if it is valid, what can we say? It could be that here we have a 1, right? Or it could be that we have a 2, 2 or 3, 3. We don't know exactly what is the actual possible padding length, but at this point, if we know that padding oracle says it's valid, we know that the last block, this particular plain text block, has either 1, 2, 2, 3, 3. Very likely it's 1, but you get the idea that valid padding means the last byte is valid. Okay, the last few bytes follow the rules of padding. Okay. Now, what happens if a random block is not, of course, going to satisfy your padding requirement? You're generating a random block R. Why would it randomly satisfy this property? If it is not satisfying, what can we do? We can do a simple trick. We can start changing this byte 1 byte at a time, right? We could just increase this by +1. Check whether the updated padding oracle is valid, meaning the updated call to the padding oracle is valid. If it is, then we can stop. Okay. If it is not, we keep continuing until we exhausted all possible 256 possibilities. At that moment, we know for sure at least one of the attempts will have a valid padding oracle, because if you change a byte here, right? If I change something here, it will affect over here, right? Something will happen here. But if I keep on changing all possible values for this particular byte, then I must be able to generate all possible values for this byte as well, right? That's how the XOR works anyways, because I'm just keep on trying. What if the byte is 1? I check that. If it is not good, I try with byte 2, check here. So I try all possibilities, and therefore, at some moment, my resulting padding will be valid. So Oracle will say it is a well-formed plain text. Okay, that's the idea. So I will now show to you this particular technique of generating a random number or in such a way that the padding oracle is valid. Let me show the algorithm for you now. What I'm going to do is, given a block, right, ciphertext block, I'm going to find another block or such a way that the padding oracle is saying, yeah, you have a valid combination. Okay, how do we do that? We just call the generate random bytes function, which I have discussed earlier. We'll give you a bunch of random bytes of a given block length. And then, as I shown on the whiteboard, I take the last byte. I keep changing the last byte. As you can see here, I increment it by 1 and keep on trying the padding oracle for any error message. As you can see here, I'm just trying the last byte, all possible last byte values, right? Until the padding oracle says, yeah, you have a well-formed plain text. At that moment, I return the random bytes. So that's basically what I'm doing here in the in this portion of the code, which generates a block or such a way that padding oracle will say I have a valid padding. Okay, with that, let's go back to the whiteboard now and talk about the next step. Let's assume for a moment that we got a valid padding, and we don't know whether it's ending with 1, 2, 2, 3, 3. How can we now find out what is the actual padding length? Okay, for that we can make use of a simple trick that we have discussed during the length computation, right? We computed how many bytes are padded. How did we do that? We started modifying here. We checked whether padding oracle is valid. If padding oracle is saying valid, that means this particular byte is no longer part of the padding check. Otherwise, we would have gotten a padding error. So we keep changing byte by byte over here until we get a padding error. The moment we get a padding error, let's say I got a padding error as soon as I modified here, that means I know these 2 bytes together are part of the padding calculation. That's how I find out whether the resulting plain text is ending with 1, 2, 2, 3, 3. This is exactly the same idea we talked about when we computed the length of the padding. Okay, so what is the big deal? Why do we need the length of the padding? If you know the length of the padding, we can do very easily one more thing now. Let's say the length of the padding turned out to be 1 for a moment. Okay, so can I now tell you what is the byte here? Of course, you can easily tell because you found out the length is 1. Okay, so all you have to do is take this value 1, which is here, right? This is 1, and you know this value. You XOR these 2 values, and how do I compute this value? This value is nothing but XOR of this value and this value. So we are able to get this last byte easily. Okay, what if the last 2 bytes are 2, 2? Okay, again, we know that because we computed the length by modifying by 1 byte at a time until the padding error occurred. So let's assume for a moment it turned out to be 2, 2. Again, the same idea. We can take the XOR of these 2 bytes with these 2 bytes. That will give us these 2 bytes. Okay. So this is basically the technique to learn as many bytes as possible just using the trick of generating a random block OR and keep calling the padding oracle until OR followed by Y is valid. Once you have a valid OR followed by Y, we can start modifying 1 byte at a time of OR until padding oracle failed. At that moment, we know exactly whether the plain text end with 1, 2, 2, 3, 3. Again, the actual plain text is not 1, 1, 2, 2, 3, 3 because we are computing against a random OR. But that doesn't matter. Once we learn the these bytes here, right? These are the true bytes. We can take these bytes and go back to the original picture. What we learned is essentially that let's say we are taking this block as an example. What we learned is we learned over here at this point, okay, some number of bytes. All you have to do is take these bytes and XOR it with the previous block to get the correct plain text. Okay, that's important to note. I will talk about it in the code in a moment. Okay, now let me show to you how I compute the last few bytes of the inverse permutation. First, we generated a random block OR such a way that oracle OR followed by block is valid. And now let me talk about more precisely the last word oracle. We start here. Last word, you're given a block, right? The first thing we do is we generate a random block OR using the technique that I just discussed. And then we call another function called last word oracle, which takes the random bytes on the block and invert the permutation or AES. Okay, so how are we going to do that? This is basically the same as the length padding calculation algorithm, which will compute how many bytes are padded. We talked about this algorithm in the previous segment, so I request you to watch that. Once you find out the length, it's now very easy. All I'm going to do is take the previous block, the random block, right, and XOR it with the pad length. That will tell us the, let me show you on my whiteboard, much easier. So I take the length, let's say the length is 1, and I take the random byte last value, last byte, and I XOR these 2 things to get this particular value. That's exactly what I'm doing. Suppose the length is 2, 2. That means I have a little for loop, take each byte here, XOR it with the corresponding random previous byte to extract the corresponding output here. Okay. So with that, we can now go back to the code and explain to you this portion. Okay. This is exactly what I'm talking about. We find out the padding length using the previous segment discussion. Please watch the previous segment if you have not. And all we are doing is take the previous block and XOR it with the pad length to obtain the inverse permutation values. Okay. Once you have the inverse permutation values, it's easy. All you have to do is go back to the original ciphertext structure, XOR it with the previous block. All right. Let me now wrap that up very quickly. All we learned today is how can I find bunch of bytes over here, right? Which is basically the decryption of the ciphertext without knowing the key, just using the padding oracle. How did we do that? We generate a random block R such that padding oracle says R followed by Y is valid. Of course, a random R will not satisfy it right away, so we keep changing the last byte. All possible 256 bytes are tried, and therefore we will eventually get a good R such that padding oracle will say valid. And you may wonder, why will this be true? We are trying all possible values for that byte, right? That means the XOR will also try all possible values. Therefore, at some point, it will end with either 1 or 2, 2 or 3, 3 or whatever. At that moment, we know we found the right R. Once you find the right R, then we can go back to the previous segment and use the number of padded bytes algorithm to figure out whether did we pad 1 or 2 or 3 and so on. Once you find the number that we padded, then we can just use XOR trick to find out this portion of the output. Okay. The next segment, I will show to you how, given this portion, how to recover the remaining parts. Okay, that's all. Thank you very much for your attention.